Hello, in this video I'm going to be looking at inferential statistics, so I'm going to be covering parts from the Year 1 AQA course as well as the Year 2 AQA course for psychology. So what I'm going to first do is walk you through an example of the sign test and show you the steps of how to conduct this test, because this is the only one out of all of the statistical tests you look at that you will have to conduct yourself, potentially in an exam. And this is AS level content. So what I'm going to do first is give a bit of a scenario, so we've got a background to be then able to test whether what I am going to put forward is supported by the statistical data that we collect or not. So I'm going to say that I'm interested in the level of talkativeness in terms of how many words participants say 1 minute after drinking coffee compared to drinking water. So I'm going to put forward a directional hypothesis. Now this can also be known as a one-tailed hypothesis. And I'm going to say that people who drink coffee will become more talkative than people who don't. So I'm giving a direction to my research. That is what I'm expecting to find. And then I've got a null hypothesis as a backup in case my directional hypothesis is completely incorrect. And I'm going to say that there'll be no difference in talkativeness when participants drink coffee or when they drink water. And I'm going to have two conditions in this experiment. This is an experimental research, and I'm looking for a difference in how many words, so that's my measure of talkativeness, participants are going to say 1 minute after drinking coffee and 1 minute after drinking water. So the participants are going to be taking part in both conditions, so we can note that this is a repeated measures design, and my data is going to be nominal when I code it. So if we look at the criteria for a sign test, you'll see that we've got to be looking for a difference rather than an association. So I've put this nice table in at the bottom where you can see all of our tests of difference in the middle, and whether they're in independent groups or matched pairs or repeated measures. Then we've got all of our correlationals, so that association research on the right side, and our levels of measurement. Now, if you look in the table from the proposal of research that I've put forward on that previous slide, you will note that I have decided I'm going to do a repeated measures design because my participants are going to take part in both the coffee and the water condition. Okay, my data will be nominal, so we've got to have data that's organised into categories to meet the criteria of the sign test. And we've got to be looking for a difference rather than an association. And I am looking for a difference because, remember, I'm looking at talkativeness and looking at a difference in whether people are going to say more words in the coffee condition or the water condition. And that's my measure to test for the difference. So if I draw your attention now to this values table, you'll see that I've got all my participants on the left side in that first column. Then I've got coffee and then I've got water. Now in the coffee, on the first row, you'll see I've got the number 60. That is how many words my first participant said when they were asked to talk in that 1 minute period after they drank coffee. And then water, they said 45 words in that 1 minute period. So what we do is take 60 from 45 and we're left with 15, which is a positive number. So we put a plus in that sign of difference column. And we do this for all of the tests. So you have to go through, you might want to pause the video if you wish to have a go at this yourself. And you've got to work out whether we're going to be left with a plus or a minus. You put a minus in if you have a negative number. Okay, so this is the table with all the different pluses and the minus in. So the step 2, after you've done the coffee minus the water, is to work out how many pluses are there and how many minuses are there. You'll see from this table that we have 8 pluses and 1 minus. So that leads to our next step. We know how many pluses we've got and we know how many minuses we've got. And that's classed as our nominal data. That's how we've turned the two middle columns, the coffee and the water, into nominal by putting them into pluses and minus. So From the plus and the minus, whichever has the smallest value, we call that S. So we have only got 1 minus, but we have 8 pluses. So our S value is going to be called 1. And then we have to then look at a critical values table and compare that to see whether we have statistical significance or not. Now you will also notice that participant number 9 is highlighted because this participant scored 50 in terms of they said 50 words after drinking coffee in that 1 minute period, and they also had 50 in terms of the words they said after drinking water. Now this is a problem for our research because they did not show any difference. So what we have to do is exclude this participant as though they didn't exist. And now we are actually left with 9 participants which show a difference between the two conditions. If they don't show a difference, we have to exclude them. And this applies to the sign test and Wilcoxon. But if they were to score, let's say, a participant the same in a related t-test, you would keep them in the data. So this is the critical values table I have. Now you'll note at the bottom I've got here, for the sign test, P has to be less than or equal to 0.05 for statistical significance. And you'll see that my critical value is called 0.05. So that is the one that we're going to be getting from that table, this purple table on the right side of the screen. And our calculated value, that P, is what we called S, which we noted was 1 from the previous slide. So we already know our calculated value is 1. And what we've got to do is look at this table and decide what number are we going to pick out from the criteria. So you'll see at the top it says level of significance for one-tailed test, level of significance for two-tailed test. Now my hypothesis was a one-tailed test because I said there was going to be a direction. I believed that there'd be more words said when participants drink coffee compared to when they don't. So I gave a direction, which means we have to look under the one-tailed test at the top, and we're using a 0.05 significance level. And here we've got to make sure that our n, so this is our number of participants, is 9 and not 10, because we had to exclude that participant, number 9, who scored 50 both times and therefore did not show a difference. Okay, so we've removed them. And what we can see now is that from the table, when we look in that row next to number 9, the number of participants of 9, that first row has 1 in that column where 0.05 is, okay, and that is now our critical value, so that's 1. So what we've got to decide is, well, is our p-value less than or equal to 0.05? And what we can say is yes, it is, because our calculated value was 1 and our critical value was 1, so they're exactly the same. Remember, they can be the same for statistical significance. This is an example now of how you would write up your results from that experiment. So what we would put here is that the calculated value of 1 is equal to the critical value of 1 when n, so that's the number of participants, is 9, using a one-tailed hypothesis and a significance level of 0.05%. Therefore, the results are significant and we must accept the alternative, so that's that one-tailed, that directional hypothesis, and reject the null hypothesis. So, this table now shows us how we can choose a statistical test. So what is likely to happen is that you'll be given a scenario or some background and an experiment will be conducted. And what you've got to decide is, well, is the researcher conducting something related to independent groups, or are they doing repeated measures or matched pairs? And that will determine what type of test they are conducting. Are they looking for a test of difference, like I was, where I was comparing the number of words said after drinking coffee to the number of words said after water? Or are they looking for a test of association, so correlation, something like as the number of hot chocolates decreases, the weather is warmer. Okay, so as one thing goes up, the temperature outside, another thing comes down, the sale of hot chocolates, for example. And the way to remember where each of these statistical tests fits in the table is by using this acronym of carrots should come mashed with swede under roast potatoes. So that determines each of the first letters and helps you to remember where these tests fit. And we also have this thing called the rule of R. Now, all of the statistical tests in that table at the top that have the letter R in them are those where the calculated value, so that p-value, must be equal to or more than the critical value for significance. Now, you would be told in a question whether your p has to be more than or equal to 0.05 or p has to be less than or equal to 0.05. But if you know that all of those tests with an R in, and the word more also has an R in, hopefully that will help you remember that the p-value in that instance has to be more than or equal to 0.05 for statistical significance. And all the ones without, so the sign test, Mann-Whitney and Wilcoxon, don't have an R in. They have to be p is less than or equal to 0.05 for statistical significance. And also something to note is that the calculated value can be called the observed value. So we now have a little bit on probability and significance. So the directional or non-directional hypothesis, so whether you say that there is a direction to your research or that there will be a difference, that is what a non-directional will say, can sometimes be referred to as an alternative hypothesis. That's just another name, and it can be written as HA or H1 because it is alternative to the null. So the null is where you're saying there is no difference between whatever the conditions you've got, and that can be noted as H0. The statistical significance determines whether we're accepting or whether we're rejecting those hypotheses. And for significance in statistical tests, we work on this basis of probability rather than certainty. We can't claim that we have actually discovered significant difference or correlation because 5% of the time we're saying our result is down to chance. And this, we usually use a significance level of 0.05%, that is 5%, and it's usually written as P is less than or equal to 0.05, and that P is standing for our probability value. So this means that the probability that the observed effect, so our result, so that's that calculated value, occurred by chance is equal to or less than 5%. The use of statistical tables. Now, when we look at a statistical table, what we've got to determine for where we're looking at that table, so we know exactly where we need to look on it, is have we used a one or two-tailed test? What is the number of participants? So that normally appears as n on the table. And for some tests, we actually use degrees of freedom instead. And the standard level, as I was saying, is 0.05%. So you'd look at that column, and 0.01, so this is 1%, this is much stricter. This is usually used in studies where there is a human cost. So things like drug trials, for example, where it's going to benefit society significantly, we need to make sure we're using a stricter level of significance. And the lower that p-value is, that calculated value, the more statistically significant the result will be. Now, for degrees of freedom, this is calculated differently to how n is, which is just the number of participants, and this applies to a chi-square and a related t-test. So degrees of freedom can be worked out by doing r minus 1 times c minus 1, and r is standing for rows and c is standing for columns. And you'll see below I have a table, which is from an exam question actually, which I've just put in here. And this is Greensville and Brownton and considerate behaviours at the top, and we've got litter in the bin, dog on a lead, riding the bike with care. So what researchers are comparing in this question is considerate behaviours between these two towns. Okay, so what we're going to do is R minus 1. So how many rows do we have? And these are just the rows with numbers in. So you'll see that we have 2 rows. So we've got to do 2 minus 1, which is 1, and columns minus 1. And we have 3 columns: litter in the bin, dog on leave, and riding the bike with care. So 3 minus 1 is 2. We do 1 times 2, which equals 2. So the degrees of freedom here, if you're asked to calculate them, would be 2. Now, you do not need to remember that degrees of freedom formula. That will be given to you in the exam or on a question. It will be there. So don't worry about remembering that formula, but you need to know how to apply it if you're asked to calculate it. I now have a slide on nominal, ordinal, and interval data. So nominal data is data represented as categories. So these are things that you can only fit into once. You can't have, for example, more than one favourite football team. You only fit into one category. Same with your eye colour. You can only fit into one. You either have brown eyes or blue eyes, okay? And then you've got ordinal data. So this is something that is ordered, and it doesn't have equal increments between each value. So if there were 2 judges and one judge gave a score of 8 out of 10 to a dance performance and another judge gave 4 out of 10, it doesn't mean that the person who gave 8 thought it was twice as good as the person who gave 4, because it's a subjective kind of measure. Similarly, the person who gave 4 doesn't think that it's half as good as the other judge gave. These raw scores would not be used in statistical testing, and instead they are ranked in an ordered way, but that is not something you need to know how to calculate. And then we've got interval data, which includes data that has units of equal, precisely defined measure. So this is things like when you're measuring somebody's height using a tape measure. It's a very strict kind of measure. It could be a temperature, so a thermometer. And below I've got some examples, and your job is to work out where they fit. So you might just want to pause the video and try and work out which these fit into. Okay, so the time taken to run 10 kilometers is an interval measure. So that is because time, it has equal increments between each thing. The difference between 1 second and 2 seconds is the same as what 2 seconds and 3 seconds is. Participant sense of confidence on a scale of 1 to 10, that is ordinal data. You're on a scale, that is subjective. People's favourite colour, that is nominal. You can only have one favourite colour. Behaviour charts kept by a nursery classifying children as good or naughty, that is also nominal data. So you're representing these children in categories of either good or naughty behaviour. And then judges in a dance competition give scores based on performance, that is ordinal data. So a type 1 error is called a false positive. So this can be remembered by being optimistic. So it's an optimistic error. This is where we truly believe that we have found statistical significance when actually we haven't. So what we do is reject the null hypothesis. So if I take you back to my example of, I've got the null hypothesis, which is there'll be no difference in the level of talkativeness when participants drink coffee and when they drink water. So let's say I reject that, and then I say that I found statistical significance because I truly believe I found a statistically significant result. I've got a direction that participants who drink coffee will talk more, and I accept that, and I've got rid of my null hypothesis. But actually what I've done is just been too optimistic, because in reality that null hypothesis is actually true, even though I believe I found statistical significance. So you've been falsely positive, you've been too optimistic, and that is known as a type 1 error. A type 2 error is the opposite of a type 1. So we accept the null hypothesis, so I accept that there is no difference between participants who drink water and those who drink coffee in terms of level of talkativeness, and I reject the alternative hypothesis, which was my direction, to say that participants will talk more if they drink coffee. And I genuinely believe I found no statistical difference at all. But this time I've been actually too pessimistic, and there really was a statistical significance all along, and there was a difference. So this is known as a false negative or pessimistic error, and these different types of errors will happen up to 5% of the time. Okay, so I've now got parametric testing. So have a little think, what are the criteria for parametric tests? You might want to pause it and have a think. And here's my table. So what I've done is highlighted that bottom row. So these are known as parametric tests. The unrelated t-test, related t-test, and Pearson's R. The other tests above are known as non-parametric tests. Now these parametric tests are seen as the most robust and sort of the strictest type of test you can have. And the criteria is that there must be interval level data. The data should be drawn from a population which would be expected to show a normal distribution. So that's your bell-shaped curve. It looks the same as what an IQ normal distribution would look like. That is how the data from a population should fit. And there should be something called homogeneity of variance. So this is just the idea that the data is similarly dispersed. And when we talk about dispersion, we're talking about the spread of data. And that relates to the range and the standard deviation. So we'd expect to see similar scoring in each condition. We don't want extremes. We expect the dispersion to be similar. And one way to ensure they are similar is to use a match pairs or repeated measures, because we're using the same participants, and it's generally assumed that the two groups of scores have a similar spread. Okay, so here's your statistical test table again. Make sure you have this noted down. It is super useful and it is relevant for the next exam question that we're going to be looking at now. So this exam question is taken from A-Level Paper 2 from June 2017. This is the scenario first of all, and then we'll look at the exam question itself. So psychologists wanted to test whether listening to music improves running performance. The psychologists conducted a study using 10 volunteers from a local gym. The psychologists used a repeated measures design. Half of the participants were assigned to condition A, so that's without music, and half to condition B, which is with music. All participants were asked to run 400 meters as fast as they could on a treadmill in the psychology department. All participants were given standardized instructions. All participants wore headphones in both conditions. The psychologists recorded their running times in seconds. The participants returned to the psychology department the following week and repeated the test in the other condition. Okay, so now we have the question. The researcher used a directional hypothesis and analysed the data using a related t-test. The calculated value of t, where degrees of freedom, represented as df, equals 9, was 1.4377. He decided to use the 5% level of significance. And then we've got, give 3 reasons why the researcher used a related t-test in this study, and, using table 2, explain whether or not the results are significant. You'll see also below table 2 it says the calculated value of t must be equal to or greater than the critical value in this table for significance to be shown. So if we first of all look at the first part of this question, which is give 3 reasons why the researcher used a related t-test in this study, you want to be having a look at your table with all of the different statistical tests are. And look where it says related t-test, because if you look in all of those in the row and the columns, you'll see that for the row it's got interval level data. Now we know that this study has used interval level data. You might want to refer back to the item, that scenario, because the researchers were measuring the time taken to run 400 meters in seconds. We know that they're looking for a difference because participants are taking part in both conditions. They are looking for a difference whether music positively impacts and makes people run faster, or whether the participants will be quicker when they don't listen to music. And we know that it's repeated measures design because they're taking part in both these conditions. So that is why the researcher has decided to conduct a related t-test. And then you've got to explain whether or not the results are significant. So what this requires you to do is look at this table of critical values. Now, where it says question 16, you'll see that it says the researcher used a directional hypothesis, and we know that that is also called a one-tailed hypothesis or one-tailed test. So you look at the first row, and it says we've got a 5% level of significance. So you would go for 0.05. And then we know that degrees of freedom is 9 because it tells us above. And we can see if we go across, it is 1.833 for our critical value. Now, if we just check that rule again, it says the calculated value of t must be equal to or greater than the critical value in this table. Well, our calculated value is 1.4377, which is not equal to or greater than 1.833, which means we have not got statistical significance. So are the results significant or not? The answer is no, and you would explain why when you look in the table when you compare the calculated to the critical value. So here's the mark scheme for you to have a skim over. It was all AO2 marks. This is application, and you'll see we've got a difference between the two sets of data is predicted. The data is interval, a repeated measures design, and then we've got whether the results are significant. Result is not significant. And then the explanation is because that calculated value of t, that 1.4377, is less than the critical value of t, which is 1.833 at the 0.05% level for a directional hypothesis where degrees of freedom is 9. So you need to make sure you're integrating all those parts of the question, even the degrees of freedom and the fact that it's a directional hypothesis, into that answer. Okay, thank you for listening and best of luck with your revision.